Hsiao-Yu. And she works with Professor Josh Tenenbaum and also Dan Yemens from Stanford University. And she is a rising star in the field of 3D perception and common sense for embodied agents. So she's going to tell us about the research that she's been doing recently. So Fish, you have the floor.
Okay, thanks, Alan, for the wonderful introduction. So hello, everyone. My name is Fish Tung. My Chinese name is Hsiao-Yu, and Hsiao-Yu in Chinese share the same pronunciation as little fish. So that's why I come to this name as Fish. So today what I want to share with you is mostly my research work done during my PhD. And as an extension to that, I will also talk about what I'm currently working on as a postdoc. So in my PhD work, I try to build agents that can learn several aspects of visual understanding of humans while moving and interacting with the environment. My research covers topics including 2D to 3D understanding, object manipulation, visual reasoning, and thinking. So today in this talk, I will hope like people will have some interactive question answering. So unfortunately, now I cannot see you guys and the chat window. So if you have questions, I will try to stop a little bit in the middle so you can jump in and then ask the question. Okay.
And I'll keep track of hands being raised.
Okay, okay, yeah, that's perfect. Or just interrupt me, like no problem. Okay, yeah. Okay, so since today's talk is about moving agents, I want to start the talk by showing you a video recorded by an actual moving agent, a moving toddler. So here we can get a baby, put a GoPro on him, and let him run. So here is one such video I found on YouTube. So as the baby moves around in the scene, this actually causes object to become larger or smaller. Object can come in and out of the field of view. There's a lot of occlusions. Objects are usually not in the center of the image. And often you cannot even tell what the objects are based on a single image. Although the video is so noisy, somehow the baby can make sense of it. The baby can do a lot of things like navigating or playing and can learn a lot of things from this type of noisy inputs. It doesn't get dizzy, which is really intriguing. So today what I want to talk about is how we can build a moving agent that can do the same. I want an agent that can work and can learn under camera motion. So how can we achieve this? What we know from neuroscientists is that the brain has strong ego motion stabilization mechanism that can cancel out the effect from eye and head motion. And after ego motion stabilization, most people believe that the brain established a stable scene model despite camera motion. Ego motion stabilization for me is a very important problem because without it, it's just very hard to understand what's happening from these videos. And that is because in 2D, camera motion is entangled with scene appearance. Here, I will show you a concrete example to demonstrate this point. So here are 3 video frames of me taking a video of a toaster oven on the table while holding my cell phone. So the toaster oven is not moving. The only thing that is moving is my cell phone, the camera. Here, I can mark the corner of the toaster oven, and as you can see, the corner actually moves in the image space. So in 2D images, static object actually move during camera motion. And not only that, object can change size or disappear at occlusion. Object do not persist, so there's simply no object permanence. But this is problematic, right? Because that basically means even if you can detect perfectly in the 2D pixel space, you will still have difficulty figuring out how many objects are there or whether these objects are moving or not. If you apply 2D CNNs directly on top of these pixels, they will also suffer from the same entanglement issue. You will see object features moving all over in the 2D feature map. This is a problem exists in current 2D CNNs that get dealt. But then the question is, how do we learn a model that can do ego motion stabilization and can handle camera motion? Can we learn it by training our model on large image dataset like what people usually do in computer vision? Probably not. Because to do well on these data, you don't need ego motion stabilization. In these internet images and videos, the objects or the actors are already centered and well framed. So to recognize them, the model can simply find useful pattern in the image that will get them the correct answer. Of course, some people try, they say, okay, if you do camera stabilization, it helps improve your action recognition performance, but there are still many works that show the model can do well without doing this. Then, if this is not the data we're going to use, what data should we use, and how can we get the frame stabilized? Actually, in robotics, since people need to deal with moving agents, they have realized the importance of equal motion stabilization long ago and have developed this amazing tool called SLUM. There has been an insane progress in SLUM for the last 40 years. So what SLUM do is, given a set of images, so a video, SLUM will estimate the camera motion and fuses RGB or RGBD views into a 3D point cloud map of the scene. So as you can see in 3D, scene and camera motion are disentangled, and as a result, objects persist. Objects don't disappear and they don't change size during camera motion. There is also recent advance in nerve that can do SLUM. Here I show the bundle adjustment nerve from Lin et al., which can recover depths and camera pose from egocentric video. Again, the recovered objects persist after stabilization. They don't move or change size with cameras. But what is the problem of SLUM or this new type of nerve model? Well, the problem is that there's no model completion, which means that to generate this nice 3D point cloud with all the chairs, tables, and objects on the table, you need to go around the scene quite a lot. You need to see the scene from all the views. Look at the blue trajectory of the cameras. These are all the places the camera has been to. Next time I show you another new office scene, you need to do this again. You need to walk around, take all the images, and do your optimization again, because the model cannot imagine anything from a single view. And this is what I mean by it does not do a model completion. So to extract complete 3D model of a scene from a single image, there has been many recent work that try to integrate learning into this 2D to 3D inverse graphic process. Here I show one of my prior results that use neural networks to predict 3D human meshes from videos. So with learning, the model can learn to predict a complete 3D human mesh, despite seeing only one side of the human. And not only this work, there are many other ongoing works that can infer complete 3D meshes, point clouds, or voxel occupancy from static image. Recently, there's a rise in interest for implicit function, and people have shown that the implicit function can generate beautiful and detailed 3D occupancy or images. However, despite humongous interest in 3D representation, we still don't know whether these detailed 3D reconstruction are the right representation for agents to act and reason. The problem for 3D mesh, point cloud, voxel, or implicit function is that they do not solve for the right end task, which is recognizing the world and acting competently in it. For example, if today my task is to catch this rabbit, capturing the curvature of the ear of this rabbit does not help, but knowing that the rabbit is soft and not slippery does. However, such information is already discarded in a 3-point cloud or a 3D mesh. Indeed, Ronnie Brooks also say that predicting accurate occupancy or 3D reconstruction maybe is not the right end task for the robot to act. And actually, this is back in 1991, when most researchers focused on geometry and 3D reconstruction and not deep learning. Actually, there are many recent work in RL that shows the robot can learn to act from raw image input without going through 3D. So the question is, what should be the right visual representation for the model to see, understand, and act in the environment? Do we want 3D or not? Do we want to use 3D representation or not? So my tentative answer here is yes, we need 3D, but with featurized 3D representation that maintain learnable features that can be trained end-to-end for a final objective. Here we will use 3D voxel grid, but one can also use 3D point cloud or 3D mesh. The point here is that we not only want to capture the geometry, but we also want to put learnable feature vector at each 3D location in the voxel grid, and the feature should be decided by optimizing for a final objective we care about, for example, manipulating an object. So the features can capture semantic information much more than just occupancy or RGB. So in this talk, I will show you the results from my own works that support this answer that we need 3D feature representation. To do this, we will going to integrate the equal motion stabilization technique from SLUM into neural network to handle camera motion. So in this talk, I will introduce how we use 3D and ego motion stabilization as an inductive bias for deep neural network. And with the model, with the bias, our model can learn to parse video capture under camera motion into the 3D representation I just mentioned. And to show you the importance of this, I will show supporting evidence in 3 critical directions that we wish the robot can do well. So it will be perception, manipulation, and reasoning and language understanding. Okay, so next I will jump into the detail as how I get this 3D feature representation. But here I just want to stop a little bit to see whether people disagree with me or people have like suggestion for this solution.
I'm not sure I want to waste your time, but given the lab that you came from, maybe you would comment about the Shepherd experiments that show that people take linear time to rotate an object in their heads.
Yeah. So that is interesting. So I think later on in my work, I will show I can also do a very similar operation as the Shepherd rotation. The thing I'm not sure is whether this rotation should be linear or not linear, because you don't know whether that is a constraint for the hardware in our brain or that is a desired feature we want to capture. Yeah, but we will talk about something similar in the later of the talk.
Okay.
Okay, great. So let me dig into the detail as how we can get this 3D representation from images. So I will start by talking about the architecture, the representation again. So here we will try to capture 3D information with 3D feature maps that I show on the right. A 3D feature map has 3 spatial dimensions and many feature channels. So if you remember in CNNs, we have 2D feature maps, but here we just add one more spatial dimension to it. It's a 3-dimensional voxel grid, and at each XYZ location in the voxel grid, there's a long feature vector describing the geometry and semantic information extracting from the corresponding 3D location in the world scene. So different from previous 3D representation that aim to capture the geometry and only the geometry, the 3D feature map maintains latent features, and these features will be decided by the model by optimizing for an end task. This 3D feature map will be the representation bottleneck of geometry-aware recurrent network, GRNs. So GRN will take 2D RGB or RGBD string as input, lift that into this geometrically consistent 3D feature map. It is end-to-end differentiable and can be trained with different end tasks. So given the first frame, GRN will first transform it into a 3D feature map using a differentiable 2D to 3D unprojection operation. The unprojection operation does not contain any parameter to learn. The goal here is to bring feature from a 2D feature map into a 3D feature map in a differentiable manner. We will further apply some 3D convolutional layer on top to refine the features. So that's called this refined 3D feature map 3D memory. So our model now sees one frame, and now it constructs some sort of 3D memory of the scene. When another frame comes in, we would like to put the information from this frame into our 3D memory. However, if we do a projection from this frame, which is captured from a different camera view, after a projection, the 3D feature tensor will be sitting in a different coordinate system as our memory. So we somehow need to figure out their angle, and orient it and align it. So what we do to figure out the relative angle between the 2 coordinate systems is that we try to orient the incoming 3D tensor with different angles. And then we will do an inner product to compare their similarity. And this similarity, we can normalize it and get a distribution over possible angle. So the angle that get the highest score will probably be the relative angle between the 2. So once we figure out the rotation and translation, we can orient the tensor and then update our memory. To highlight the importance of this operation, here I will show you some animation to show this. So let's take a look at this toaster oven video again. If you apply standard CNN on top of it, you will find out the corner of the feature will be in different location in the XY location in your 2D CNN feature map. So the feature actually moves with camera motion, although your toaster oven is there, it's not moving. And today, if to aggregate information, many works run RN on top of these features, such as 2D RN or conval STM. However, since these features are already in different XY location, this will make aggregation very hard. And as a result, some of the network will start to cheat by memorizing the statistics in the data set instead of learning to aggregate the information in the proper way. This means if you use such latent state to learn something, you won't be able, or it will be very hard to generalize under different camera motion since everything looks so different. But in GRN, instead of doing the aggregation on the 2D feature map, we will try to project it into 3D features. So we want to operate in the 3D feature map. And when the new frame count, you will try to estimate the related camera pose and then orient your tensor and update. So when the new frame count, estimate the related camera pose, orient the tensor and update. And as a result of such an operation, although the features are in different XY location in the 2D feature map, they will end up in the same location in the 3D feature map. So what GRN is trying to do is it's trying to ensure there's a one-to-one mapping that can establish between the 3D world and the 3D feature map. And to summarize a bit, what GRN do is it try to explicitly disentangle camera motion and scene appearance. And as a result, feature can be easily integrated over time. It persists over time. It don't move or change size during zoom in, zoom out, and it don't disappear at occlusions. So GRN ensure there's like object permanence in some sense. So okay, so now I will stop a little bit since this is like a bit complex contents in the talk.
So Tim.
Yeah, I've got a question, Fish.
Yeah.
The thing that you haven't explained to me, which is sort of key, is the projection and unprojection, because you're saying those are not learned, I think. Are they just like a max pool or an average pooling, or surfaces are only on the front that you can see, but your projection and unprojection are sort of done column at a time, I assume. So how do you do those?
Okay, let me see. Yeah, so what we are using here is we are using the standard pinhole camera model. So in the pinhole camera model, if you know the intrinsic of the camera and you also know the location of the camera, then you can kind of like shoot a ray that goes through one of the pixel, and then everything that touch the ray, you try to color it with this feature over here. And if you have depths, then you don't need to color everything. You only color the scene that is close to your depths.
And how do you aggregate then over multiple depths? And then how do you disaggregate when you unproject?
Oh, I see. So you mean like if I have multiple view, how do I aggregate, right?
No, I mean you've got multiple green pixels there, multiple green voxels there, for example.
Yeah.
So how do you combine all those green voxels to get the green pixel? And then when you're unprojecting, how do you extend the green pixel to fill all 5 green voxels?
So we can talk about unprojection first. So unprojection is like you try to shoot a ray from your camera to the green pixel. And then if you keep extending your ray, then it will eventually touch several of the voxel grid. So what you do is everything that touch this shooting ray, you try to color it into green, since you don't know which one is actually the green.
I see. So you color them all, and then for unprojection, for projection, you do like a mean pooling or something. You average them all the green ones.
Oh yeah. So let me see. Oh, the projection is okay. So later on, I will talk about the projection.
Oh, okay.
In the projection is more like I would try to project these features from different depths. So maybe this depth I try to project and I get a feature map. This depth I also project. So I get several projection map, and then I just treat all of them as my features. So for a projection, it's like I fix my depths. Maybe it's like here, so I get yellow, green, blue, red, and I also take another one maybe here, maybe here. So if I try to project from this depth, then I get green, green, blue, blue. So I get two feature map. One is this one and one is this one. Okay, then later on I will have an animation and maybe I can
Sounds good.
Yeah, great.
But it is that unprojection and projection are not exact opposites of each other, right? Unprojection is a little
Yeah,
dumber.
they're
Projection.
they're not exactly the same. Yeah.
Okay, thanks.
And Matt had a question too.
Okay.
Oh, my hand's still up. Sorry.
Yeah.
But
Yeah.
I will ask, so these are kind of like more like graphics primitives. Are they implemented by actual ReLU units or something like that? Or are they just operations that are done in the network and you found a way to differentiate through them?
Yeah. It's more like you try to write down the graphic operation like unprojection or projection in like PyTorch or Tensor, so it's kind of like differentiable. So there's no ReLU. The operation we are trying to use here is like camera pinhole projection.
Yeah. So these don't. I'm just saying these don't have. They don't actually have a neural implementation. They are functions that you've added to a neural network.
Yes.
In
exactly.
software. Okay.
Yeah.
And I'm sure your animation will disambiguate all, but just to jump the gun, if you have partial transparency, does this mean that your unprojection gets confused or corrupted?
Transparency
In the world.
Okay, that is a good question. So we actually have two setups. One is like assuming you don't know the depths. So if you don't know the depths, then what you would do is you will just put the features all over along the ray. If you have depths, then you will only put the feature around your depths. So I think the transparent issue you talk about, maybe it will be more like, okay, maybe this green one means transparent pixel. So you put the transparent pixel all over along the ray, and then you let the network to figure out where there are objects or no objects.
Okay.
Yeah. So I think there's some probability that it will get it, since it's not like exact graphic de-rendering.
All right. And similarly, objects that have holes will not confuse the unprojection operator when you unproject along a different angle because you had some ego motion.
Oh, yeah. So actually, I will go into that. So I think that is a very good question. So like, imagine you see this bowl, you only see this side of the bowl. How do you know the bowl is it actually has a hole, and then try to impend the rest of this stuff? So later on, we will introduce a task called view prediction. And through this unsupervised view prediction, the model will learn to complete the object. So it tries to do this a model completion.
Okay.
So that although it only see one side of object, it try to imagine the back of the object.
All right.
Yeah. Okay.
Go ahead, you can keep going.
Anyone want to ask more questions? Or I will just continue. Oh, let me jump. Okay, so
continue.
Yeah. So we are here. So just to summarize a bit, what I do is I try to explicit the disentangle camera motion and scene appearance. So our model kind of know object permanence. So far we only talk about the neural architecture, but not the objective which we can use to train the network. So to infer a complete scene representation, just as people have asked, the model not only need to put the feature in the right location, it also need to try to imagine the missing information from the current view. So it needs to do some model completion. To achieve this, we introduce a task called view prediction, which will force the model to learn this. So the task goes like this. So given a set of images viewed from different viewpoints, the task is to imagine the image from a query camera position. The idea is that if the model can predict well the scene from any viewpoint, that somehow means they already complete the missing information from the input view, right? So actually the task is self-supervised because it does not need any human annotation. Instead, what we need is just a moving agent. So the agent will move around the scene, take images from different viewpoints, and record the corresponding camera position and That is the data we are going to use. So here I will describe the method. Our model will first take all the input views and then their camera position, and then use GRN to construct this 3D feature map. And once we have a query, once we have like a query viewpoint where we want to answer the image, then we use the query viewpoint to rotate the tensor and then project the 3D feature map into 2D. So here is the projection operation. So I will try to define like a depth and then project the feature from the steps. And I can actually set up several depths, so I get several feature maps, and I will just concatenate them together. So once I project the 3D feature map into 2D feature map, I can go through some conv and deconv layer to decode it into a target image. So your training is given the image and camera position, and then your objective function is you want to output this image from another view. So to highlight the importance of having this 3D bottleneck, we try to compare our model with the generative query network from DeepMind, which also use the same view prediction objective function, the same data. The only difference is this model does not maintain a 3D feature bottleneck. Instead, it uses a 1D or 2D feature representation to extract it from 2D convolution layers and pooling layers. So everything is the same. The only thing is the bottleneck. And now we are going to see how this bottleneck is going to affect the results. So here I show some results. In the first row, I show prediction results when the training and the testing data have similar distribution. So we train a model on scenes that always contains 2 objects. And here I try to test the model. So on the left, I show 3 views as inputs. So I will take these 3 views, give it to the model. And then on the right, I show in video what the model predicts from a viewing sphere. So you can see both model, our model and this GQN2D model, both generate some reasonable predictions. Our model performs slightly better, but not dramatically. However, the interesting thing is if we test this model on scenes that contain 4 objects, which both models have never seen during training time, then our model performs significantly better. So our model consistently generates images with 4 objects, but for a 2D one, while it takes input with 4 objects, they still see 2 objects. So this is what I mean by that the 2D model will start to cheat by memorizing the statistics in the training data, since aggregation for them is not straightforward, so they just find some heuristic that will give them some kind of reasonable output. Okay. Yeah, so we indeed show this 3D bottleneck is very important for generalization in view prediction. And now our model can complete the missing information from a single view. But in order to act or learn something useful, just generating beautiful images is not useful. What is important is for the model to see objects. So for the model to detect objects, we can add mass RCN on top of these 3D feature maps. So while standard mass RCN take RGB images as input and try to predict 2D box and segmentation mask, here we will adapt the model to take 3D feature map and try to predict 3D box and 3D segmentation mask. And we use the model to learn detector in several different domains, and the model works well. So on the top, I show detection result in photorealistic self-driving car scene generated in Carla simulator. On the left and on the bottom, I show result in real-world office scenes captured by Kinect. And we can use the detection results for a robot to manipulate object on the table. Okay, so here I will stop again. So I just wonder whether people want to ask questions regarding view prediction or detection.
Perhaps you could help us understand the difference between what used to be called volume carving, where you would, if you know the camera homographies, you just project the scene into a block of voxels.
Yes.
And then you whittle, you carve away parts of the voxels that are not consistent with the foreground of the scene. So is this essentially what's happening, and then the neural network is providing smoothing?
Yeah. So I think that is the key point. So you will have image feature coming from different camera viewpoint, and what you try to do is using this graphic operation to put feature coming from similar 3D location together. Although they are in maybe different image and different XY position, you try to like put them into the same 3D location. And then after you put all the features, all the information you have into this 3D feature Vassal grid, you use another layer to try to do this imagine or inpainting to make the 3D feature map complete.
I see. Okay, yeah, so that's the inpainting stuff. And what happens when the camera estimates, the camera motion and direction estimates have error?
Yeah, yeah. So I think that is a very good point, and I think that is one of the strengths of our network, because we are using network to also learn about how to estimate related camera pose. So if you have this error, maybe our neural network would be possible to fix that error, although you have error in your camera motion. So if you do standard graphics, then everything needs to be accurate. Otherwise, it would be weird. But in our case, since it's neural network is learning the features and learning the refinement, even if you have small error, the network would be like a possible solution to fix that error.
Because it's jiggling around the camera trying to find a simpler projection or a more consistent projection. Yeah. Okay.
Okay, cool. So I will try to move on. Okay, so now our model can detect object in the scene. What I want to talk about now is how we can use it to achieve few-shot object recognition and 3D pose inference. So since we have an embodied agent that can move around, we will let our agent to run around in the room and detect all the objects it can find in the room. So when the agent runs in the room, it will find several objects. They are actually in different locations and maybe looks slightly different, but they actually look similar. So the idea is like, if you can try to summarize the object into a few categories based on their look, then when the labels come in, you can quickly propagate the label based on your summarization. For example, here I can, in the 3D space, I will feel like, oh, these two orange objects looks pretty similar. So if today I tell you the object on the right is called orange, maybe you can also propagate and then say, oh, maybe this object on the left is also orange. But the challenge here is that objects can look similar in 3D, but they might look different in 2D. So if you try to compare object in the 2D feature space or in a 2D feature or 2D image space, you will likely to get incorrect result because you will think these two sofas looks completely different. So here we don't want to use 2D features. Again, we are going to use 3D feature representation we talk about. So we will try to infer object-centric feature representation from this image about these two sofas. And then since the 3D feature maps will be complete in 3D, no matter which view you infer them, and it's in 3D, you can explicitly rotate this feature and compare the features of two objects. Also, as a result of rotating and comparing operation, the model gets to know the related pose between two objects without 3D annotation. And inferring related poses between objects is actually critical for object manipulation. And we both get to correspond object together, and we also get their related pose at the same time. So here I will go into more detail. So what our model is trying to do is it will try to detect all the objects in the scene and try to cluster them into 3D prototypes. We will use the self-supervised view prediction task we introduced to initialize the feature. Once we initialize a feature, we will use a trained object detector to detect the object in the scene. Then we will start to build our prototype dictionary. So if you see something you have never seen before, then yeah, that's added into our prototype dictionary. If you see a new object, you try to rotate it and compare it with our current prototype in the dictionary. If it doesn't match, then we will create another new stuff for it. And then you can just keep going on and adding more objects. And you can parse all the scenes and then get all the objects. And at some point, maybe you will find some object actually looks similar to one of the prototypes you already have in the dictionary. So in that case, you don't create a new one, but instead you try to do some optimization to kind of like average the features between these two. So here I show some of the unsupervisedly learned prototype and scene parsing results. So on the bottom, I show some of the learned visual prototypes. So you can see this prototype actually look like an orange. This look like a lemon. And then we can also parse the scene and then label like which prototype this object corresponds to and what is the relative angle between this and the prototype template. We also try this on the more complex data in Carla, and we can see our model can find out different cars with different shapes. We also try this in the real world office scene. We try to build some template for single objects, and then we can see our model can redetect these objects in the world and also label their poses. Okay, so since our model now can cluster object into a few prototypes, we want to see how this can help in few-shot word learning. So in the training data, we provide 2 labels for each object category. So this is very little. And then we want to test whether the model can correctly label the instance presented in the test data. So with this very limited data, we compare our model with the baseline that used ResNet feature trained on ImageNet data. So the first one used ResNet feature to retrieve nearest neighbor in the training data and copy paste the label. The second one fine-tuned the ResNet on this handful of labels. And as you can see, our model performs significantly better than these baseline, although it has never been trained on so many images in ImageNet. So this few-shot results is very intriguing. And we think to ourselves, can we disentangle further? So now we learn some object 3 concepts, but there are also sub-object concepts like color, shapes, and texture. So in later work, we actually do this. We try to disentangle the whole object features into shape and texture feature using adaptive instant normalization that people proposed in 2D image operation, but we just operated it in 3D. We test the model on VQA, and we want to see whether it can learn with few label. So our model will see some example objects in the training data scene that are densely annotated with attribute and object boxes. So our model first try to disentangle these objects into style embedding, shape embedding, and then build this prototype dictionary of style and shape. Okay, so now when the question comes in, we will first use a semantic parser to parse it into a function. And when the image comes in, we will first disentangle them into different vectors and then start executing the function. Okay, so now the question is, find a broccoli. So here, this is the broccoli prototype. And then you try to rotate and compare. And maybe you will find one of the objects. Actually, object 2 is the broccoli. And then you can keep executing it. So you can also train like a relation detector that can detect relation. So we find the object on the right of the broccoli. So this is the object 3. And then last, we try to read out what is the name of the color. Okay, this feature actually is called red. So that's our answer. So with this model, we show our model can answer diverse and complex questions. And we also compare with previous work, neural symbolic concept learner from Mao et al. This is actually from Josh's lab. So what NSCL do is it uses the similar semantic parser and function execution, but it operates on 1D embedding as opposed to 3D. And since these 1D embedding can only be learned through end-to-end optimization, so it needs tons of labels to learn. While our model can leverage 3D structure to learn about 3D object and shape concepts, even before the label comes in. So that's why our model can afford very efficient word learning to associate with this ready concepts. Okay, so here I will stop a little bit and see if people want to ask questions. So this is really about like if you try to represent object into 3D, you can rotate and compare them. So your compression will be in a 3D space instead of in 2D. So that will make it more possible to correspond object with similar shape together.
Yeah, I've got a question if no one else does. You showed an object detector,
Yeah.
with a little red box on the 3D objects, but is it a 2D object detector? And how are you running it on those 3D objects?
Oh, for our model, all the detections are in 3D.
So back, go a couple of frames back to where you have a little red box inside the cube.
Red box in, oh,
There.
this one?
What do those
Oh.
represent?
Oh, okay. So this is actually some feature learning technique we use in this paper, but I just don't have time to talk about the detail, but you can check. So
Okay.
yeah,
So
so this is some
object
feature learning.
detector running on that. You
Yeah.
don't have some sort of preliminary object detector running on it.
Yes. Yeah.
Okay.
So these objects are from this detector. Yeah.
Thanks.
Okay. Yeah. Maybe we can continue. Okay. We talk about learning concepts and VQA. So next. Okay, we talk about VQA and then we compare with model that don't use 3D bottleneck, and we again show our model can learn with very, very few training examples. So the work I just talked about is more about scene grounding and object detection. In our CVPR 2020 work, we also show we can do scene generation. So what we are trying to do here is, given a sentence, we build a generator that can generate the feature map from the sentence to a 3D feature representation, and then we can render images from these 3D feature map. With the generator, we show our model can generate scenes with given a language description. And since the generation is in 3D, we can use the generated scene to determine whether a language description is plausible or not plausible. Because in 3D, objects have sizes, it's easy to detect 3D non-intersection, and there's no ambiguity on spatial relationship. So it becomes very easy if today somebody asks you whether an object can fit inside the other, whether a car can fit inside a person, it would be very easy for you to answer. And this type of spatial reasoning ability is largely missing in current computational model of language and vision. Actually, Alyosha effort says that we are training model to cheat on the test because these 2D model, they can answer very complex questions there in the training data, but they don't know basic things regarding intuitive physics. And with the generator, we can also enable agent to follow language instruction, since now it can understand and imagine the 3D goals from the instruction. So I will skip the detail due to time constraint, but you can check more detail in our paper, in our CVPR paper. Yeah. So far we have talked about how our agent can learn to detect and recognize objects and concepts. Here I want to discuss how we can further allow the agent to act. For the agent to be able to act, it is critical that we not only see objects, but we also know how objects can move according to their action. So here I want to talk about how we can use the proposed representation to learn object dynamics. To predict how things can change according to an agent's action, there are many video prediction works that try to predict change in the pixel space. For example, here I show this visual foresight from Chelsea Finn et al., where they predict future frames given an input image, and they use the video prediction for the agent to plan and act. However, the prediction is not accurate, it's kind of blurry. Why? Because in 2D, objects and their appearance can change dramatically during occlusion and when objects change their pose. And the video prediction model just need to capture all these big changes caused by prediction and occlusion artifacts. Unfortunately, occlusion and object pose change happens a lot during object manipulation. And actually, there are also other works that try to predict object translation and rotation instead of predicting change in the pixel space. The general method is to combine object-centric representation with graph network. Here I show this nice work of propagation network from MIT, which can predict complex object dynamics accurately. On the bottom, I show recent work from Halsey from Berkeley, which can handle diverse object shapes. Despite these results are impressive, these models are still restricted to motion prediction in 2D. So to cover more general object dynamic, we would like to think about how to extend these models to 3D. And there are actually existing work that can predict object motion in 3D. However, the main restriction of these work is that they require the camera to be fixed at a nice viewpoint. For example, here, this is a photo from the dense fit snap paper. For the model to work, the camera needs to be in a top-down view. The prediction will fail if you move the camera to look from the side. The main reason why they fail to generalize to other camera viewpoint is mainly due to the image encoder they are using. So all of them are using 2D CNN-based image encoder whose outputs are view dependent. So that's why they cannot change their input view. So here I propose a method that can remove these two restrictions existing in current vision-based object dynamic models. So here's my model. So given the input, again, we will use GRN to get a 3D feature map. And then from the map, we will use detector to detect all the objects and run a graph network on top. The graph network will try to predict the 3D rotation and translation for the next time step. So with the predicted rotation and translation, we can translate and rotate the object feature in the 3D feature map to generate the feature map for the next time step. With the architecture, we show our model can predict complex object dynamic in 3D that contains multiple objects. Our model can work with input from any view and can use any number of input views. So here on the left, I show results when using only one view. And on the right, I show results that use two other views. The prediction is pretty consistent across different views. And our model not only can predict object 3D motion, it can also render simulation video from any viewpoint. So here I show we can project the enrolled 3D feature map and then render them into a video. We also show we can use it to predict object motion during pushing, where the model condition on some robot action. Okay, so here's some quantitative comparison with model with different feature. So in the first one, we only use XYZ 3D space. And on the second one, we try to add some image feature. So as you can see, although you try to add some more information from the image space, if you didn't do it correctly, then it actually increased the error during your prediction. And if we use the 3D feature map, it actually reduced the prediction error quite a bit. So using the learned dynamic model, we also run like an MPC on top of it for the agent to learn to push an object to the desired location. And again, when you set up the real robot, you don't need to adjust your camera so it matches with your training. Any camera viewpoint will work. So you just put your camera at wherever you want. So we show our model can push the object into a target location. We also further include obstacles, since our model now know how objects move in 3D, and it also know how to predict 3D location for the obstacles. It can try to push the object to a target while avoiding the obstacles. Yeah. Okay, maybe I'll finish all of that and then we come to the question. Okay, so here we kind of have a model that can allow the agent to do some pushing task. But imagine how this per time stack predictor will work if today the case is to grasp an object. So in order to build a robot that can grasp the bottle using the method I just mentioned, we need to predict the force and position for all the fingertips at every time step. So the model needs to know how each of these fingers are in contact with the bottle, how much force are applied at every time step. And this is much harder than the pushing example. However, what is hard in the fine-grained granularity may be easy in a coarser granularity. So what if today we try to predict how object will move in a fine-grained timescale? Instead of predicting in the fine-grained timescale, we can try to predict in the coarser timescale. And coarser timescale actions are called primitives. And indeed, robot learning is more about primitives. So why this is the case? Because if you try to predict primitives, then learning becomes very easy and can happen with a few examples. So here So because here, what you will need to do is just selecting the right primitives as opposed to predicting the action for every time step. And the most impressive work in robotics, like GraphNet and Tosin bots, they are all about learning primitives as opposed to learning a closed loop policy that try to map image to action. For example, in the 60 GraphNet, what the model is trying to do is from point cloud, it tries to propose some graphs position. And then once you decide which graphs you want to try, everything afterwards are hard-coded. So you basically just manually craft, hand engineer the motion of moving your gripper to the target grasp point and grasp it. So there's no learning after you decide. So the learning is only happen to choose which grasp you want to do. Once you choose it, everything is not learning. But all of these previous works are only about grasping. So the question here is, how do we extend this idea to general skill learning? For example, maybe you will want a general pick and place with fixed and firm graphs. And maybe you will want to push different objects of different granularity, and maybe this test you don't even know how to model the dynamic of the objects. So these tests are harder and we don't have a good framework for them. So now I'm going to show you a more general way of learning with primitive with the 3D feature map we talk about. Okay, so here we will have some primitive for a task. For grasping, maybe for some object you want to grasp from the rim, some object you want to grasp from the center, some object you want to grasp from the handle. So assuming we have all these primitive, and then we will call them a library of behaviors. And now I will have an object. So the question is, if today I have this new object, how do I decide which behavior is correct that I can pick up this new object? So what we are trying to do here is, for each behavior, we will use the object-centric feature map built from corresponding objects and treat them as a retrieval key for the new object. When the new object come in, we will extract its object-centric features and then use the object-centric feature to trigger which behavior should be applied on this new object. And the good thing about disentangle the whole policy learning process into primitive and this retrieval is that now each of your primitive can use different input. So maybe some primitive only use 60 posts, some primitive maybe can use depth or RGBS input. So in short, what we are trying to do here is we say, maybe we can have a selector that look at dense and rich features. They are view independent. And then we can have some behavior representation. They're kind of like abstract and concise. Okay, so here I'll just show some of the results on grasping and pushing. So for grasping, we designed different primitives as trying to grasp object bounding box from different orientation and translation. So here I show some of the behaviors. So for example, for behavior 1, only 2 objects is successful. So I put in red box events that are kind of like successful. So although each of the behavior can only handle a subset of objects, by combining them together, we will show we can get very high results. We also designed a different behavior for pushing. Okay, so here I show some comparison on the grasping task. So here, the first one is only using 60 posts. The second one is trying to add some image feature to it. So you can see if you add image feature, yeah, because since now it can now know what object I'm trying to grasp, it actually increased a bit the successful rate. We also tried this. So this is actually our initial hypothesis that it will work. So we initially think like, oh, we have this nice 3D feature map. Maybe let's try to learn something that go from the 3D feature map directly to the action. But actually, this model is very hard to train because the 3D feature map has 4 dimensions, and the computation is super high. So this model actually doesn't work well at all. And then we also compare with some baseline that use that try to propose different graphs. And we see by combining different very naive primitives, our model can actually perform much better than these other methods. I want to mention a bit is like for DexNet, although it's like a very strong baseline, it always tries to grasp from a top-down view. But for our model, we can incorporate primitives that try to grasp from the side. So that's why we have higher successful rate, because we know how to handle objects that need to be grabbed from the side. Okay, so here's some of the example in the simulator. And we also show the model can easily be trained on a real robot. So here are robots trying to grasp different objects in the real world. We also show result in pushing. So again, you can see if you only use abstract, you will hit this ceiling since you don't know exactly what the object looks like. And then this 3D tensor regress to action, it never works. And if you try to use a selector, you use a 3D feature as a selector feature, then it works much better than these other models. Okay, here are some videos of pushing. We also compare if we build a selector with 3D features versus 2D features. And if you use 3D features, it performs much better than 2D features, which can be affected by camera viewpoint. We also use it to build a robot that can do plating for different objects. Okay, so just to capture some of the key of this 3D feature tensor, it is robust to camera viewpoint change, and it can learn from self-collected data. With this 3D bottleneck, we show better generalization, and then we also show it supports spatial reasoning. And here are my collaborators during my PhD. Okay, so this is my PhD work. And then here I want to also mention a bit what I'm working on during this postdoc. So most of the scene I have talked about is mostly about scene that happen in a static. It's like object in a static scene, so nothing is moving. Although I introduced some of the work that do some future prediction, but I think it's still not like super good, and it only handles rigid object. So what I'm trying to study in my postdoc is I try to figure out what is a general way to learn about object dynamics, not only for rigid object, but also for liquid, squished, closed, different type of objects. So what I'm working on is what should be this representation for intuitive physics. And I think intuitive physics is very important for all the above direction I've talked about. And it's also well studied in psychology. So what I'm trying to do is borrowing from some psychology insights, we build a very diverse data set called fission. So the fission benchmark covers several dynamic scenes that is commonly used in psychology tests. And then what I'm trying to figure out is what kind of model can predict well the outcome of these prediction. The model I'm trying right now is called graph network on particle-based representation. Here I will skip the detail, but I just want to jump right into the conclusion. Is that we find out human can actually do pretty well on this benchmark. We also try all existing 2D visual features model, and they don't actually work quite well. But I actually tried these 3D aware particle-based model, and they can achieve pretty good performance that is close to human. And of course, here I want to emphasize like the comparison is not fair because we assume we have the 3 ground truths, and then from the 3 ground truths we do the prediction. So here one of the key problem I'm trying to figure out is trying to bridge the gap to go from 2D image to these particle representation. During the postdoc, I also study questions like curiosity-driven models and information-driven. So now if you have an agent, how do you know what you want to try on the new object to learn about it? Also, I study how do we figure out objects' functionality and their structure and how to manipulate them. And some of the work is in collaboration with people from MERL, like Ota-san and Alan. Okay, so here's the end of the talk. So thanks, people, for attending. Yeah. Thank you. Yeah, so maybe we can go to like QA if people want to ask something.
Very interesting, Fish. Thank you. Are there any questions from the audience? So I have a question.
Okay.
So obviously you said you have a volumetric representation that has additional channels. It's not just, for example, an occupancy graph or thing, but additional information. I guess the implication of your system is that you can rotate those features by some kind of a resampling, and they still work correctly. Is that right?
Yeah. I think that is exactly the point.
Okay, interesting. So they can be transformed by a rotation matrix, and they still maintain their usefulness for the tasks.
Yeah. So that basically means like if you see a cup with maybe handle on the right, you don't need to retrain your model to figure out, oh, if I have a cup handle on the left, it actually works similar to handle on the right. You just rotate it and then it just transfers.
Interesting. I see Tim has a question.
Yeah, I was wondering what are some of the failure cases or weaknesses of the model? Because all the examples you show, of course, look great, and so the question is, where is it? What does it struggle with, and what are you thinking for fixing those problems?
Yeah. So I think there are two major issues. One is about computation and memory. So as you can see, this 3D voxel, it actually takes a lot of computation because it's like 4D tensor. And usually when you train this model, it's significantly much slower than 2D CNN approaches. And also, like usually you only use batch size like 1 or 2. So it actually takes like much higher computational requirements comparing to 2D CNNs. And the solution I'm trying right now, one is trying to sparsify this voxel grid. So maybe you can try to store your feature with sparse tensor. So you don't say, oh, everything including the empty space, I store some feature. For empty space, just label saying there's nothing there, don't store anything there. So using sparse tensor is one solution. Another solution is this particle representation I'm trying right now. So for a particle representation, you actually don't waste your computation on space that is like kind of like empty. So what I'm also trying right now is how do you convert from voxel representation to particles, and when do you need to convert particle back to voxel representation? So I think these are the solutions. So one is maybe fixing your data structure so it's more efficient. The other is trying to transform this dense representation at some point to the sparse one. And the other question I see is about data, because most of the large scale data we have now online is like static image with some label. But what these models really need is like a more natural data collected by a moving agent. So you need like an agent that really like move around and collect tons of images for you. And we just don't have like a diverse and complete enough data set for this type of input. Yeah.
Great, thank you.
And Noop has a question too.
Yeah, hi, Fish. Nice talk. So I have a question regarding like you have these future prediction and dynamic scenes and stuff. So all these kind of induce a lot of uncertainty in the prediction framework. How do you account for the uncertainty or the norms in the model, predictive uncertainty and such? How do you account for these in the model that you learn?
Yeah. I think that is like a very good question. So far, I haven't touched much on that part, but I think that is like super important. So I think one way to do it is when you build this dynamic models, you try to add like a stochastic component to it. So you say with the same input, maybe I want to generate a distribution of possible output. Okay, maybe you can try. These doesn't have much uncertainty. Okay, so imagine you have a tower and the tower falls down. Maybe the tower will fall down like to the 0 degree, maybe it fell down to 30 degree or minus 30 degree. You are not sure, but all of them are possible. And I think what you need in your model is you need to say, I want to generate not like a fixed output. I want to generate like a distribution. And I think VAE is like a good architecture to generate a distribution of output.
Yeah, okay.
Yeah.
Any other questions? Comments? If not, then I think we can thank our speaker one last time.
Great, thank you.
Very, very nice work, Fish. I have to think more about how to put this stuff into more of our robot projects because I think you've got a lot of great stuff here.